Hello, today we will discuss the multinomial theorem. So we know that x1 plus x2 all the way to xm to the power of n is equal to the repeated multiplication of those terms n times. But let's try to find a pattern by extracting some expansion rules. Alright, so similar to how we did in the binomial theorem video, here's rule 1. Then we have the expandable terms in accordance with rule 1, as we did in the previous binomial theorem video. And we're going to generalize rule 1 to rule 2 by multiplying the outside terms. Then we're going to define rule 2 as we did in the previous video. But is there a limit on the number of expansions? The answer is yes. And we get rule 3, which limits the number of expansions. So in summary, we have rules 1, 2, and 3. But we only need rules 2 and 3 because rule 2 is a generalization of rule 1 if we include 1 in the set of Q. And rules 2 and 3 mean that if we start with x plus y to the n, then we will end up with m to the h terms after h expansions. Each term will be of the form of repeated multiplication of each of x1, x2 all the way to xh of length h, of course, after h expansions. And we could expand a total number of n times. So for example, when n is 4 and m is 3, let's trace a path to x, z, z, y. And we're going to do that by choosing first the y, then we're going to choose the z. After that, choose the z. Then we will choose another z, choose another z, and then we will choose an x term on the end there. And we have reached our target. So this means that we could reach any sequence of a string of 4 x's, y's, and z's. And we'll show another example in the next slide. Alright, so here's another example of tracing the path to zx, yz. From right to left, we'll start with z, then y, then x right there, then z. And we have reached zxyz, target reached. And let's do a third example where we do y, 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 x. So we're going to first begin with x, and then we're going to choose a term with y on the end, on the left end, then another y on the left end, and another y on the left end. And we have reached our target string of x's, y's, and z's, or in this case, only x's and y's. So we can trace a path to any sequence of n of x1, x2 all the way to xh after n expansions, and each possible sequence is separated by a plus sign. As you will see, this gives rise to a formula. And due to the properties of multiplication, we can actually aggregate these terms. So it only matters how many x's, y's, and z's we have in this example, where x1 is x, x2 is y, and x3, or xh, is z. So, yeah, order does not matter when you do multiplication. And this gives rise to a formula here, where you take the sum over k1 plus k2 all the way to km is equal to n of c sub k1, k2 all the way to km, where c sub all that stuff is the number of ways that we can choose k1 of x1, k2 of x2, all the way to km of xn. And we'll see that that's equal to n choose k1, k2, km. That is the multinomial coefficient. And it's going to be equal to that stuff on the right side. And the multinomial coefficient simplifies to n factorial over k1, k2, km, all factorial. And on the end there, we're multiplying by that x1 to the k1, x2 to the k2, all the way to xm to the km, and we have the multinomial theorem right there. So that is the end of this video, and thank you for watching. Don't forget to like and subscribe, because it really helps. Thank you.